Okay, so good morning, everyone. Good afternoon, as far as my internal clock's concerned. Thanks very much to the organizers for inviting me to this interesting session. I did finish this talk since midnight. The reason I did that is because I wasn't really sure who was going to be assembled here, and so yesterday I tried to get an idea of what level to pitch things at, so the talk isn't as polished as it might be, but I hope it's going to be something in there for everyone who's in the room. And so I did decide to start quite way back with something that's covered in a review article ages ago, the basics about constraint models and emergent gauge fields, and then perhaps the most important result, which I'd like to share with this audience specifically, and then some unpublished work which we are wrapping up at the moment. And so all of this is part of a large long-term research program on topological phases of matter, as they are now known. And it turns out that in condensed matter, emergent gauge fields are surprisingly common, and often they arise from constraints. And so these ideas then that or the models that we come up with often appear in one form or another in different communities in a different context. So under the name of kinetically constrained models, they've become quite popular in quantum dynamics and magnetic frustration. They go back decades. And the aspects that people are interested in tend to be quite different. And what I'm trying to do today is perhaps give a little bit of an overview of the conceptual commonalities. And then there's one thing having an emergent gauge field, and then there's another thing asking what are the physical consequences of having that. So in the same way that you can ask, given I've got a metal, what interesting phenomena does it display? What interesting phenomena do topological phases of matter, interacting topological phases of matter exhibit? And the thing that I would most of all like to emphasize is that you can get an emergent quantum electrodynamics in a very simple Ising model, which turns out to have the fine structure constant as an undetermined parameter. And if you work out what the fine structure constant is, it turns out to be a tenth, so a lot larger than in our ordinary QED. And so one of the things that I'd like to motivate people is to think about actually realizing such a system and studying it, ideally in a hybrid version where you then also couple normal light to it. This is quite an ambitious long-term research goal. So I'd like to close with, I think, what may be somewhat lower-hanging fruit, which is the motion of the same fractionalized type of defects in 2 dimensions. And I'm going to give an example of how you can get tunable sub-diffusion in 2 dimensions and how many different sort of theoretical ideas and concepts can be used brought to bear for that particular problem. Okay, so I'm going to start with a very basic introduction. Please stop me if you don't understand things, otherwise the time is completely wasted. Okay, so constraint models. So this is something which has really been a staple in condensed matter physics, at least since the discovery of high-temperature superconductivity, when the famous double occupancy constraint and good spiller projection came up in the Hubbard model. But even going way, way further back than this, there have been dimer models. This is like 1950s, where you basically just say, okay, my basic degree of freedom is not a single site-based variable, but a link-based variable. There are ICE models where you say, on a given site, I constrain the configurations of the 4 bonds which are attached to it. In frustrated magnets, there's the idea that you can have many different energetically identical but symmetry inequivalent states. So then you can project onto those and ask what is the energy physics there. And then more recently, what has become very popular is the Rydberg blockade. So for instance, the PXP model, which I'm sure all of you are more familiar with than me. So it turns out back in 2000, we already had the PXP model in this 2-leg diamond ladder. You can convince yourself easily that if you flip those 2 dimers to be horizontal, then you can't flip the neighboring dimers. So a plaquette of dimers is only flippable if the 2 neighbors are also flippable. So that's just PXP. So we called it the 2-leg diamond ladder or the 3-leg Ising model at the time. So these things, we didn't ask any questions about dynamics. So that's really a completely different strand, but you see that the kind of models, the kind of concepts that you have really are persistent over decades. Okay, so I'd just like to give you an actual worked example of how gauge fields emerge from very simple degrees of freedom. Okay, so that's really the next slide. So I'm going to start with water ice, talk about spin ice, and then about the vertex language. These are completely equivalent, and the idea is just to give you a feel again for how these things occur in different settings. So we like explaining phases of matter and phase transitions using water, which is a really bad idea because water is very anomalous. One of our favorite phase transitions, water, the liquid to gas transition is a first order symmetry sustaining phase transition, and so on and so forth. And what's worse, ice itself, so the solid is actually only partially ordered, right? So sodium chloride would be much better, that's fully ordered. So what's ordered in solid water is the oxygens. They form a fourfold coordinated lattice, but the protons which bond the oxygens together are not ordered. Rather, they are arranged so that out of the 4 proton bonds, 2 protons sit close to the oxygen and 2 protons sit far away. And then if you draw a little box around this, what you see is that in water ice, you can actually identify H2O molecules. So water ice is really a disordered or partially ordered tiling of water molecules. There's a system known as spin ice, where the spins live on a tetrahedron, and somewhat helpfully, I've already drawn this tetrahedron here. So if you draw an arrow from the midpoint to the bond to the proton, then you see that there are 2 spins pointing in and 2 spins pointing out. These are known as the spin ice rules for obvious reasons. Okay, but it turns out to be actually more useful to think of these degrees of freedom actually as living on the bonds of the lattice. So I'm going to take the dual lattice of the lattice on which the tetrahedron sit, and then I've got, again, 2 arrows pointing in and 2 arrows pointing out, or 2 protons sitting near and 2 protons sitting far away. So these are all equivalent formulations. This is the ice model, this is the frustrated easing model, and this is a 6-vertex model. So, and all of them encode the same low energy degree of freedom, low energy states when you apply the ice rules, the spin ice rules, or the what will turn out to be an emergent conservation law for this flux. Okay, whether or not such constraints give rise to interesting new structures is a question of details. There are many models you can write down which where the pictures look exactly the same as this, but which don't actually have the level of interesting emergence that ice and spin ice have. Okay, but the important thing is if you've got all of these exponentially many microstates and you want to write down a long wavelength theory, then the question is whether any of these constraints actually alter the long wavelength theory as compared to the case of a paramagnet where the constraints wouldn't be there. If you can identify conservation law, you can coarse graining, keeping the conservation law intact, and then you may end up with an emergent gauge theory. And then concretely, the way this works is that these arrows, which I introduced before, you can think of as a lattice vector field. If you say there are 2 arrows pointing in and 2 arrows pointing out of each vertex, then you can write this as the lattice divergence of this vector field vanishing. And then you can simply remember what you did in undergraduate electromagnetism. You can resolve this vector field by writing as a curl of a vector potential. And that's completely microscopic, completely kosher. There's no surprises there. Then if you do the coarse graining, you need to be lucky that you end up in an interesting phase of this model. And the simplest thing that you can try is to say, I'm simply going to write the lowest order, the most relevant, whatever you'd like to call it, symmetry allowed term, which, again, you'll remember from magnetostatics is just b squared curl a squared, okay? That's the effective theory. Then you can ask, okay, if this is my effective theory, can I calculate the correlations between these arrows? And you can do this. You get emergent magnetostatics. What you find is that the arrow correlations are algebraic, so they're power law, 1/r³ in 3 dimensions. And if you Fourier transform it in reciprocal space, you get these characteristic pinch points. So these are non-analyticities, which, unlike a Bragg peak, are not divergent, but they're just a discontinuity in the first derivative. Okay, so that's it. So in other words, if all of this works, if the constraints give you an emergent gauge field, then you should be looking for these pinch points. And people have done that in the case of spin ice materials. And here are the pinch points in experiment. Okay. So you can do the same thing with water ice, and it turns out in water ice, people have also seen pinch points. And you can actually, in a relatively simple calculation, calculate the correlations between the protons in water ice. Okay, so this is where the emergent gauge field comes from. There's absolutely nothing surprising here. So none of the steps I've shown you here is in any way complicated. It's just that it took a very, very long time to actually find an example which realizes that, but I think now we know many, many examples. If you've got an emergent gauge field, you can have excitations which are charged under the emergent gauge field. Okay, so here I'm showing these very simplified versions of these tetrahedra with 2 arrows pointing in and 2 arrows pointing out. And the thing that's important is that there's a divergence-free constraint. So basically, you just arrange these things head to tail, and at every side you're supposed to think of a second string which actually crosses this. But the important thing now is if you flip a spin, then there are 2 locations where you violate this divergence-free nature of this flux field. And if you flip further spins, then you don't lead to further violations. You actually just separate these 2 places where things are violated. So in other words, the degrees of freedom, which are the low energy excitations, are sources and sinks of this gauge field. Here's a source, here's a sink. Okay, so these are charges of the emergent gauge field, and these are what we call deconfined monopoles, because in a magnet they actually carry a magnetic charge. But basically, this is one of the simplest cases that you can get of fractionalization in higher dimensions. You start off with something which has a north and a south pole, and you end up with degrees of freedom which only have a north pole, or only have which are a north pole and which are a south pole, and which can be separated. Okay, that was it. So that was the basic introduction. Now I'd like to come to the question, what happens if you add quantum dynamics? So if you want to quantize a system like this, I've so far told you classical ground states. What you basically need is a Hilbert space and quantum dynamics. Hilbert space you can do very simply in these discrete systems. You simply say all the configurations which satisfy the constraints are going to be one basis vector of the Hilbert space. And then you can ask, what is the simplest local rearrangement of degrees of freedom that keeps me within this constrained space? And that turns out to be a loop flip, because if you take a loop of arrows pointing clockwise and you revert it, then you can easily see that you never violate the ice rules or the divergence-free rules in the final state, provided it was satisfied in the initial state. So this type of dynamics was essentially first written down as a quantum model by Roxanne Kills in 1988, and it now it's now appeared under various guises, under various names in quantum diamond models, quantum ice models, ring exchange models, and so on and so forth. So the structure is always a large coefficient for sort of a classical constraint, and then a perturbative addition of quantum dynamics. You can now do the same thing. You can coarse grain this to get an effective Maxwell action, and in fact it was Mike Hermele when he was graduate student here at Santa Barbara, who did this in a very nice paper for his PhD. And then what you find is the Maxwell action, E squared plus B squared. So here you get emergent electromagnetism in the quantum model. Okay, so that's the effective description. If you now put in particles, I've already told you there are these magnetic charges. You can also get electric charges, and the effective theory turns out to be emergent quantum electrodynamics. This is different from the normal quantum electrodynamics because you've got more particles, right? So no one's ever seen a magnetic monopole in the Maxwellian Dirac sense, but in this particular emergent case, you can get both electric and magnetic charges. You can also get emergent photons. It's very tunable, so you can tune the speed of light. The speed of light depends on microscopic details. And it turns out, and this is what I'm going to explain in the next few slides, you can also tune the fine structure constant. Okay, and
so I'm confused about why the electric charge is much more gap than magnetic charge. So I thought the magnetic charge is one that involves a constraint violation.
Yeah, okay, so that's because there's a dual way of naming things. Yeah, okay. So what you're saying is correct in one of the versions, yeah. Okay, so, and the reason that I'm presenting this particular set of results to this particular audience, I think it would be really wonderful if one of the many proposals which are available for realizing such systems were actually implemented in using AMO platforms, because that's something that doesn't exist anywhere else. And it's also something that where we don't know what's going to come out. So we really don't have a particularly clear idea what happens at QED with a fine structure constant of 1/10. And the hope would be that if you actually set this up as an experiment, it's going to teach us a lot of things. Okay, so realization attempts are manifold. So there's an intense effort in material science at the moment, which is progressing remarkably well. And there are also proposals for 3D Rydberg atom arrays. I'm showing one here from Maryland. It seems that in this particular community, the number of proposals is parametrically larger than the number of implementations, and I haven't figured out yet what makes a proposal implementable and what doesn't. Okay, so what is the fine structure constant? So you all know this, and there's this famous picture here of Fermi with a fine structure constant incorrect. I'm not sure whether this is actually a fake photograph or not, but anyway, you can compare the various forms which are available, convince yourself that H shouldn't appear as a H bar squared. Okay, but basically it's a dimensionless strength of the electron-photon interaction, and you can think of it as, for instance, the ratio of the Compton wavelength of the electron to the Bohr radius, but there are many other relations that you can put it to. So the question is, what is the value of in quantum spin ice? It could be anything, so this is a general feature of these emergent gauge theories, that where they land you in parameter space is something that's, you need a certain amount of luck to land in a good place in parameter space. You can then always ask how you can tune things. I'm going to come to that as well. But it turns out that quantum spin ice actually lands in a very interesting part of parameter space. So just very briefly, if you want to determine what the speed of light, what the fine structure constant is, you need to determine either something morally like epsilon zeros, like Coulomb energy in the speed of light, or you can also have the magnetic energy and so on. But you can combine any two of these to get the fine structure constant, which is dimensionless. So even though these things are dimensional for quantity, there's this one parameter which isn't, and this is why this is the one we're going to focus on. Okay, and then I'm going to spare you the technical details. There's one thing I'd like to mention is that it's somewhat friendly to look at these frustrated systems, constrained systems, because you can look at system sizes, which would give you Hilbert space without the constraint, which is completely prohibitive. But then if you project onto the low energy constraint space, it can become much smaller. There's still a trade-off. If the low energy space is too low, you don't have enough fluctuations and you tend to go into a boring phase. So you need this to be big enough that you have something interesting happening, but small enough that you can still deal with it. Okay, so we basically, so we being Chris Laumann, as Hal Pace and Sid Morampudi, evaluated speed of light and the electrostatic energy. You can forget about the materials business, but what is universal, regardless of the realization platform, is the fine structure constant. It turns out to be around 1/10. Okay, so 1/10 is actually gigantic. It's often believed that the QED in 3 dimensions actually becomes unstable, becomes unstable at 1/5. So this is, even though it looks like a small number, is actually very close already to an instability. Yes?
Does that correspond to a solid state material?
So these two things do, which is why I said you should ignore them. This doesn't. So the 1/10 doesn't depend on, it's just the property of the constrained Hilbert space.
I see.
Yeah.
It's not realized in the solid state.
So there are candidate quantum spin ice materials where we're taking very rough estimates for the terms in the Hamiltonian, and then you get this combination of quantities. But you can immediately see if you applied pressure to a solid state system and you don't change anything else, then the speed of light changes because your unit of length changes, right? So this is why I wouldn't take these things too seriously, but a dimensionless quantity doesn't change in the process, and therefore this is the one to focus on.
Just a very late thought, just looking at the speed of light. So the specific heat for linear space excitations is inversely proportional to the cube of the velocity. So if it was 10 meters per second, the heat capacity would be huge, maybe literally 1 billion times larger than that potential ventilator. So it is huge heat capacity observed
Okay, so I need to think about this a little bit. You're also sitting in extremely low temperatures, right? And the total number of modes that you have is also limited. So if you're in the extreme quantum limit, so you seem to be thinking that. So are you thinking of sitting at a temperature where you essentially already have equipartition? Because that limits the total amount of heat capacity you can have, and it actually.
It needs to go below a certain temperature threshold.
Right. Okay, let's get into enough detail that it's perhaps better if we do this later, because I've got a couple of more things I'd like to say. Okay, and then, given time's advancing, you can perturb the system, so you can add things which are not particularly criminal, such as further, interactions between further neighbor spins, and this allows you to then tune the effective strength of the electric charge and the speed of light, and as a consequence you can tune the fine structure constant in a way that you go all the way to an instability on one side and in a way that you suppress it on the other. So in this plot, what I'm showing is that by doing relatively simple things, you can start from a very large fine structure constant, tune it all the way to an instability, or you can suppress it. And this is a long way away from where the fine structure constant of QED lives. Okay, so as I said, this is actually quite an ambitious program. What I'd like to do is now take many of these ideas and put them in a much simpler setting where there's already a lot of interesting physics, not quite as unknown as strong coupling QED, but where nonetheless a number of cute results can be gleaned relatively straightforwardly. So let's think about classical spin ice dynamics of classical ice constrained dynamics, where the thing that you preserve is this constraint. And now it turns out that if you, this is something here very familiar from constraint models, if the constraints are so much to essentially arrest the local dynamics, then even an extremely small density of defects can actually dominate the dynamics, right? And this is what happens in these many of these systems, is that if you have one of these defects, it can actually go around and scramble and decorrelate the system. And the simplest way of fitting or of modeling this is that you basically say, here I've got a defect, and the defect can hop around. It's still constrained by energetic considerations, but other than that, it's free to roam. And then you get a relatively simple Monte Carlo type dynamics where you simply just ask the question, can I move in a particular direction energetically, yes or no? And then with a particular temp rate, you just carry out this dynamical move. Okay, so the reason this is somewhat useful is that if you have a setup like this and you can't get rid of all the defects completely, there's still some interesting dynamics you can study, which is facilitated by the defects you can't get rid of, right? So you basically turn the feature that you've got defects into the bug that you've got defects into a feature, and then you study that. Okay, so in 3 dimensions, we just finished a piece of work which gave some very interesting results, but since 2 dimensions is easier to realize, I'd just like to define the same model in 2 dimensions, so you still have a four-fold coordinated lattice obeying the ice rules. But there's a big difference between random walks in 2 and 3 dimensions. So things like, as you know very well from, say, the physics of localization and diffusion, return probabilities are different in 2 dimensions. Densely packed loops behave differently in 2 dimensions and 3 dimensions. And in some sense, the role of local constraints is more pronounced in 2 dimensions. Another feature in 2 dimensions is that drifting exponents are much more common in 2 dimensions than in 3 dimensions, because Kostet-Saldes basically gives them to you for more or less for free. So if you look at different constraint models, like a dimer model rather than an ice model, it turns out you can get different anomalous exponents. And so what we did is we studied in such a constrained system the motion of fractionalized monopoles or monomers with the dynamics I just showed you, and then we analyzed how they move around. Okay, so the model of the 2D dynamics is the same as the one I showed a couple of slides ago for 3D dynamics. So it's, again, easily studied numerically. And then I'm going to show that there are various effective descriptions of already the essentially incoherent dynamics. And then one of the open questions, again, which I'd like to motivate people to look at, is how all of this changes if you actually have quantum coherent dynamics. And there are reasons to believe that a number of interesting things are going to happen. What we find is that there's robust long-time sub-diffusion in the monomer or monopole dynamics, which doesn't need any fine-tuning. And there are some platforms where this might conceivably be seen. Okay, so if you have a random walk, you can define what's called the loop erased random walk, where you basically say whenever you meet, whenever you reach a point which you've already met before, then that means that you've executed a loop, and then you can just erase the entire loop. And in this particular type of dynamics, what I'm showing here is the area which is covered by the random walk, and then I'm also showing the loop erased random walk. And you see that the loop erased random walk really is a lot slimmer than the actual random walk that's being executed. Okay? So there are various ways of describing such loop erased random walks. One effective one is that you say that whenever I'm in a loop, I basically treat this as if I were sitting there and waiting, essentially for the particle to come back. And then you get a waiting time distribution, which you can parameterize with this power law. And then you find that if the power beta is less than 1, then the mean waiting time actually diverges. And this is something that happens here. If the mean waiting time diverges, then you end up sub-diffusing. Okay? So this maps onto something that I hadn't been familiar with before, the fractional diffusion equation. So Nilo Palchak-Raboti, his PhD project, worked all of this out. Then you can determine the beta from direct waiting time distribution, and then you find that this fits well to a power of beta of 0.56, which is then related to the sub-diffusion exponent. And it turns out the sub-diffusion exponent is around a quarter, so it really is strongly sub-diffusive, so the root mean squared displacement grows with a power which is half that of a free random walk. Okay, you can then do some more analytical efforts, so you can write this emergent gauge theory in 2 dimensions, where it's known as a height model. In the height model, the kind of defect we're talking about can be treated in the theory of elasticity. What you need to know is what the stiffness of the surface is, what the charge of the Burgers vector is, and then and the important thing is that all of these things are tunable and depend on details of the model, and then you can again put all of these together, get an emergent entropic force between these objects, and then you can work out a Langevin equation with that interaction, and then what you find is that you get a root mean squared, as I said, which expected squared displacement, which follows this quantity, and say for the ice model it actually has, so r squared goes as square root of t, so this is the root mean squared displacement as t to the 1/4, which I advertised a second ago.
Can I try to clarify something?
Yeah.
How did you go from the monopole wandering about to loop erased random walk? Was that sort of a logical step?
So this is just an observation. You look at the random walk. So you just say the monopole moving around executes a random walk in the broader sense.
With some constraints.
Sorry?
With some additional constraints.
That's right, yeah. So it's not a random walk, but it's something which looks like a random walk, and actually it has this very strong feature that the loop erased version, makes such a big difference, much more than in a normal random walk. And so that just turned out to be a useful way of analyzing this.
Okay, so there's a monopole, there's sort of constrained random walk the monopole is doing,
Right.
and then you sort of loop erase it by hand.
That's right, yeah.
And this gives you a new dynamical problem.
That's right, yeah. I mean, this gives you a way of describing this, and this gives you a way of extracting the beta. The beta you can then stick into the fractional diffusion equation and get out the root mean squared displacement.
And what does this data eventually describe? Does it describe the actual motion of the monopole?
Yeah, that's right. So it's then directly related to the root mean squared displacement. So I'm giving you various ways of analyzing this. Any single one would be enough. They're actually consistent with each other. So you can either do this, or you can do the height model with a logarithmic interaction and a Langevin equation, so whichever one you prefer. Yeah. Okay. All right. Okay. Then there's also a frontier, an SLE description of this. I wouldn't want to stick my neck out too far on the difference between 5/4 and 4/3 based on numerics, but it does look like if you take the envelope of the random walk that I just described to Sarang, and you look at its fractal dimension, it looks to be different from what you get either in percolation or normal Brownian motion, but it looks like it's described by different SLE. Okay. All right. How can these things be realized? So there's been a lot of interest in synthetic gauge fields in AMO physics, and I'd like to advertise this as perhaps being one of the simplest ways of implementing synthetic gauge fields, simply by taking something which is only a constraint on the essentially nearest or next nearest neighbor level. So we need sparse dynamical monomers, but there are no further requirements. So this seems to be somewhat suited for near-term applications, and in particular, this is forgiving about defects and finite coherence. So by forgiving about defects, I mean the kind of dynamics I've just shown you is interesting in itself if there are defects present, and as the defect density becomes less and less, you see this kind of sub-diffusive regime more and more crisply over longer time scales. And then finite coherence, the final analysis I gave here was for completely incoherent Monte Carlo dynamics, and what happens for completely coherent completely coherent dynamics is not known. There's actually work in collaboration with Sarang we did a few years ago which started going in this direction. But this is really, again, something where unknown things can be worked out, and just increasing the level of coherence and seeing new different behavior emerge would be interesting in itself. Okay, so as I say, there are various concrete proposals. And here, there are lots of interesting physics in relatively simple settings. In particular, if you can do time and space resolved observables, you can make connections to these different pictures I gave in the last few slides. There's effects of quantum coherence that I mentioned just a few sentences ago. And the thing that I really find particularly interesting, this is work which sort of ongoing, is that what I've described to you is artificial electromagnetism, but in AMO systems, you also have Maxwell electromagnetism, right? So really the questions are, if you now couple this to photons one way or another, so the ways that you're good at coupling these things to, like in cavities or various other tools that you have, I think it's really quite an open field for what the collective behavior of this emergent and native Maxwell electromagnetism is going to be like, and I think this is a very exciting direction to do research in. And this is the kind of thing that I'd really look forward to discussing with you in the next couple of weeks. Thanks.
So thanks for a nice talk. We definitely have time for questions. I saw Jameer's hand first. And we should use the microphone, yeah, if you don't mind. Yeah.
Thanks so much. So I think I got a little bit lost on the systematics between the constraints, the type of constraints you have, and the kind of gauge theory that you get. So I can phrase this in a number of questions, and you pick up the one that you like the most, you see my confusion. So the fact that you get 1/10 as fine structural constant is an accident, or is there an understanding behind how big is that? Because in the perturbed model, right, it looks like you can make it even smaller. And a second related question is if you folks have understood a sort of theory or universality of that. So let's say whenever I have a certain type of constraints, then I'm going to get certainly those type of gauged fields theory, and they're going to have sizable couplings or small couplings.
Okay.
I got lost on that part.
Very good. Yeah, so regarding the systematics, the reason you got lost is because I said nothing about this. What I did is I gave you one example to show you how it goes as a matter of principle. And also, sort of as you were hinting at, that the systematics is you notice that you're able to cast the constraint in terms of a conservation law.
Right.
So you could have more complex conservation laws. You then end up with higher rank gauge theories and stuff like that. We now understand a lot better how to create them, right? But I think if someone shows up and just says, here's the microscopic Hamiltonian, you still have to work, to find out what the emergent conserved quantities are. They're normally, generally not obviously encoded and cannot obviously be read off just from the microscopic Hamiltonian. Okay, is the 1/10 an accident? Of course, you're sort of asking about the depth of our understanding. So I would not have been able to predict anything of its value. In that sense, it had to be something, and it turned out to be a 10th. I can't even rationalize it for you why it's a 10th. And the fact that the further neighbor interaction actually allows you to tune it tells you that there's nothing particularly stable about it. The reason that these models were not found for a very long time is that models that people looked at before, like in 2+1 dimensions, always ended up not being in the deconfined phase, so that was a little bit disappointing. But then, this is the statement I made in passing, you need a big enough space that you actually remain in the strongly fluctuating phase. So if you do this in a 3D dimer model, things, due to the lower connectivity of Hilbert space, are actually a lot more fragile. So, you know, it presumably works even better if you take a 20 vertex model on the cubic lattice, but no one's actually done this, and I wouldn't even know how to actually calculate in practice the fine structure constant. But you know, this is the first time anyone's really calculated this quantity, so we don't have any systematic understanding how it varies based on general principles.
Okay, thank you.
Rahul, did you still have that? Yeah.
Just going back to the connection between constraints and gauge theories. Now, I was just wondering if you had, any way to understand without doing a calculation whether a given constraint would produce an interesting gauge theory. And I guess this is really asking about like whether there's a non-trivial statistical phase in the constraint model.
Well, I mean, yeah, there are examples where the constraint is obvious.
Right.
Right. But as I said also to Jamir, if the mapping, any local mapping which can still be very, very complex, you need to read off. And I mean, so there are of course ways of doing this, like in classical models, you can try to identify what the projector is onto a soft spin model, and that will tell you a lot. But it can also be wrong, right? So. Yeah, I mean, I guess this is the flip side, right, of doing condensed matter physics. Anything can happen, but it's very hard to predict what will in a particular setting. Yeah.
I'm going to ask a question as the chair. So when you discussed the defect motion, you just assumed incoherent motion, and then you mentioned that there are regimes where it could be coherent. So what sets the scale for when one picture is correct and the other is not? Do you know? Or?
Well, I mean, so the reason we started with incoherent motion is because in the condensed matter settings that we looked at first, that works, and therefore you don't need to assume anything beyond that.
When you say it works, you mean
so there are a set of compounds which are sufficiently classical that doing this kind of Monte Carlo dynamics allows you to model experiments in a really considerable amount of detail. Great. Right? Yeah. Then there's what you're sort of partially aiming at is a completely separate question. When do you really need quantum mechanics to describe even the dynamics of a magnet? And I think that's a field where there have been a lot of surprises of late. And the either depressing or encouraging aspect was that if you do the right classical modeling, you can go very far. But it's a little bit like asking at which point you really need a quantum computer, and we're still looking.
So for the AMO platforms and to make predictions there, you would just start by assuming
I think this was a little bit more aimed at other NIST platforms, but I think it would, of course, be wonderful if immediately you had fully coherent motion. We could actually get data which we definitely can't get elsewhere. But the idea was sort of as the coherence improves, you actually see new physics appearing, right? So just as a search strategy.
Perfect. I think we have time for more questions. Yeah, if you could use the microphone.
So I wonder about possible observable manifestations of lattice electrodynamics. So I understand there are photons there. Is there any observable feature that would, for example, allow us to tell that a lattice photon is a photon and not just a linearly dispersive excitation?
No, a photon has two transverse polarizations.
Well, what are the observable manifestations of that?
I mean, you can. Okay, so the question how you actually determine topological phases as opposed to how you determine them theoretically in principle is quite something we can talk about a lot. So the way I would go about this is I'd actually calculate the full dynamical structure factor, which contains a lot of non-universal information. That looks a lot different from just magnons. Then you look at a 3-dimensional, say, or 4-dimensional neutron scattering results, and you ask, do they look the same? That is how it's going to go in practice once we've got 50 millikelvin single crystals of quantum spin ice. So what you would look at in an AMO setting, I think, is a completely different question, and this is the kind of things I'd like to discuss while I'm here. So what are natural observables which are optimally linked, not necessarily to the universal long wavelength physics, but to this non-universal property of, say, having optical photons, which you can then see, which might very well be then different from conventional magnons or whatever you'd like.
All right.
Maybe one more quick question. Maybe because Sebastian hasn't asked a question yet. Sorry.
Okay. So basically, two quick questions. So
I'll choose one.
2 quick questions. You choose one. I mean, the first one. I mean, often. I mean, if you have on a microscopic level quantum coherence, it doesn't mean that that it persists to the microscopic. Is there any indication that it could be important here? And the second, I mean, what are the at least expected phases that you can get at this larger alpha? I mean, you maybe some particle production instability, or
well, I mean, I'm not sure whether you necessarily. So the second one, I'm not sure you actually get a different phase as such. But what you would be looking for are things like Cherenkov radiation. It's just this idea that a photon just goes from here to there just isn't accurate in such a setting. And seeing whatever showers of photons are being emitted as a particle hops through the lattice, that's the kind of thing to look for. And what that would look like on the lattice scale, on the time scales of observations, I think are the kind of interesting questions. And the relation between short-time coherence and long-time coherence, we have to have a separate discussion about. That's not a short question.
Great. So with that, let's thank Rydberg again.